Okay, so we're taking a look at number 2 here, and the thing that we observed is that the g of x in number 2 had two things that were a little unusual. First of all, we had an extra term added, x plus. Second of all, our g was not in standard form, and because it was not in standard form, that made us wonder what is up with that. And so we have two things that let us deal with that. First of all, we have a sum rule for derivatives, and second of all, we have a reversal property for intervals. When I am dealing with area functions that are not in standard form, I always use my properties to put them in standard form so that I know what I'm dealing with. And now g prime of x is the derivative term at a time, and g double prime is the derivative of that. And that's it. Find the local extrema of g of x. Here, again, we want to use our theorems. The local extrema will occur where g prime of x changes signs. And what is g prime? It is that. And so to find those places where g prime changes signs, I'm going to set g prime equal to 0, which gives me an equation. F of x is equal to 1. And that equation will be found wherever f of x is equal to 1. And that happens at x equals -2 and x equals +4. Those are my critical points. Now, to determine max or min, I need a number line. And so I need to look at the sign of g prime. And g prime, since g prime is 1 minus f of x, g prime will be negative whenever f of x is... careful. Take a number less than 1, plug it in. That's going to give me a positive value. For example, if f of x is 0, then 1 minus 0 will be a positive 9, right? So, if you're unsure, go ahead and solve it formally, algebraically. G prime less than 0, subtract 1, divide by -1, implies that f of x is bigger than 1. So g prime is going to be negative anytime f of x is bigger than 1, which happens on the interval from -2 to +4. And g prime is going to be positive whenever f of x is less than 1, which happens from -5 to -4, and from from -5 to -2, and from 4 to 5. Yeah.
Why do you -5 to -2?
Well, my domain is -5 to +5.
Oh, okay.
So this allows me to say that there's a local max at -2 and a local min at 4. Find the points of inflection of g of x. The points of inflection are going to be places where g double prime changes signs. Remember that we had 3 ways of visualizing that. G double prime changes signs, g prime has maxes and mins, and g goes through its tangent line. Since I'm looking at a graph of g prime, looking for maxes and mins makes a whole lot of sense to me. And we see that f of x has a max right here, so 1 minus f of x will have a minimum at the same point. That's the easiest way to see it. So I'm going to say that there's a point of inflection at x equals 1, because 1 minus f of x has a min, which is g prime.
So that's not an absolute max?
This is
local max?
It is. It is a local max for f. But notice that I'm asking not for local maxes for f. I'm asking for points of inflection for g. Right? So the temptation you're going to have to resist is don't confuse f with g. F is not g. F is actually related to the derivative of g.
Okay.
Yeah. So the logic for B is that the local extrema of G will happen whenever G prime changes signs, which is going to happen whenever F crosses that line x y equals 1. Better?
No.
Number 3, which was an AP problem, was very, very similar to this. Were all of you able to click through the links and find both the problem and the solution? Okay. Yep. Let me show you how to work this. Okay. So here's my question. They don't do Form A, Form B anymore. They did that for a time as a way of trying to get around exam security problems. Now they do something different. They actually have distributed 2 forms at the same time, even within a school population. So students can be sitting next to each other and taking different tests. Yeah. What was 2D? Oh, sketching the graph. Well, all right. So putting the information together, this is from the previous class. You guys don't need to worry about any of that. So putting the information from number 2 together, we got a G prime number line for a domain from -5 to 5, and what we found was that G prime looked like so. And we didn't put together a G double prime number line, but I think we can, since G double prime was equal to -F prime, then what that means is that whenever the slope, no, that's not what we're after. Whenever the slope of, where is this? Here it is. Whenever the slope of F is positive, then the slope of G will be, the second derivative of G will be negative. And whenever the slope of F is negative, then the second derivative of G will be positive, because G double prime equals G F prime. Is what we discovered here. So that means that that G double prime is going to be negative up through 1 and positive thereafter. Think about what F prime is. It is the slope of F. And since I'm looking at the graph of F, I can see its slope. So the slope of F is positive. The slope of F is negative. And G double prime is the opposite of whatever that is. So I can immediately make the G double prime number line, which is going to change signs right at x equals 1 from negative to positive. And by the way, how should I mark this at 1? With an X, because right at 1, F has a sharp corner, and therefore F prime is not defined. Make sense? It's the visualization part, and I use this to keep my head straight, and then I go back and I find the sign of F prime from the graph. And I take the opposite. Okay. So this lets me now draw everything that I need to, except I don't have my reference value. G of what is equal to 0? Actually, my reference value, so G of x is equal to x plus the integral of x to 2 of f of t dt, is that right?
Yes.
So G of 2 is going to be 2 plus 0, plus the integral of 0 width. So this gives me a reference value, 2 comma 2, and I can see that I have a local min at 4, and I have a local max at -2. I can actually find those values. G of 4 should be 4 plus the integral of 4 to 2 of f. Notice that I'm integrating backwards there. And if I go from 2 to 4, this is a height of 1, that's a height of 3, and so the area here is going to be a half, is going to be the average of the bases times the width, that's 4. So that if I integrate from 4 back to 2, I get -4, and G of 4 should be 0. So this gives me another point right here, that's my local min. And G of -2 is -2 plus the integral from -2 to 2 of t. And going back to my graph here, from -2 to 2, I have a, what do I have? I actually got 2 different trapezoids, don't I? What a pain. So that's, the area of this guy is going to be the average of the bases times the height. That's the average of 1 and 4 is 5 halves, times 3 is 15 halves. And this guy is going to be the average of 4 and 3 is 7 halves times 1. So together, that gives me 22 halves or 11. So this gives me a max at -2, 9. And I think that's enough. I think I can draw my graph something like that. And then I can use the G double prime to check. Because if I've drawn my graph right, my graph should be concave down until 1. I should have a point of inflection right at x equals 1. And I should be concave up thereafter. And hey, look, that's pretty good.
What does that look like? Point of inflection.
A point of inflection looks like a change in concavity. So we're going from being concave down to being concave up.
So it's a straight line.
Yes. Right at a point of inflection, the graph will look very much like a straight line because at that point, G double prime will probably be 0.
Okay.
In other words, my graph should look like a linear function. So there's 3 ways to think about a point of inflection. You can think about it in terms of G prime, you can think about it in terms of G, or you can think about it in terms of G double prime. Point of inflection, G double prime changes signs. G prime is going to have a local max or local min, and G will cross its tangent line because it goes from being below its tangent line, concave down, to above its tangent line, concave up.
Do you have to know specifics
Oh, do you mean, do I need a Y value here?
Yeah.
I didn't really feel like I wanted to do one. I could certainly do one. Because I have this graph of G, I can find the value of G at any X value. So if I felt really patient, I could walk through and I could find G values at as many X values as I wanted to and just plot once. But this is a little faster. Better? Okay. Tell you what I'm going to do. I'm going to teach fundamental theorem part 1 because we need it. And we're going to do quiz tomorrow.
Oh, thank you.
So that'll give you a little bit of a chance to catch up if you need to.
Will the quiz be on fundamental theory?
The fundamental theorem. As you're going to about to find out, the fundamental theorem is exactly what we've been doing. All I'm doing is holding it. So yes, but
No.
I slept pretty well last night.
fundamental theorem comes in two complementary parts, part 1 and part 2. In some sense, they mean the same thing, but their implications are so different that we split them out into 2 parts. Part 1 simply asks, what is the rate of change of an area function? And we have actually already answered that question. We know the answer. The rate of change of an area function is, what's our slogan? The height of the curve. That's exactly right. The rate of change of the area function is the height of the curve. Part 2, that we'll take a look at tomorrow, is going to ask the opposite question, which is, what happens when I integrate f prime? And the answer is going to turn out to be, I get the change in f. So, saving that second part for tomorrow, let's consider now the meaning of this right here. I want you to have a picture. I want you to have a plausibility argument, which is not a proof, and then we're going to supply the details with the proof so you can see that it's actually good math. The picture is this. If I have an area function that gives me the net signed area from here to here. So A computes the area in red. Then asking about the rate of change of A is asking how quickly am I adding area as x increases? What is the rate at which area is increasing as x increases? And now the plausibility argument is one that I've already made, and that is if I increase x by a little bit, dx, then what I get is a little bit of extra area, and that little bit of extra area is represented in blue right there. We're going to call that dA. And the shape that I have here is approximately a rectangle. Notice I said approximately because the upper edge is not horizontal, probably. And therefore, I can say that dA is approximately equal to height times width, like so. So that if I simply divide both sides by dx, what I get is that area divided by width gives me height. And this is dA over dx. It's just another way of writing a prime x. So that what I discover is that the rate at which area is changing is the height of the curve. This is our slogan. You want to learn the slogan to help you remember the theorem. The rate of change of area is the height of the curve. Cliff is thinking. This is profound.
Hold on.
Okay. Now there's only one small problem with the argument that I've made, and the one small problem with the argument that I've made happens right here. Because my curve is a curve and not a horizontal line, the shape that I've drawn, I've argued is approximately a rectangle, but we agree it's not exactly a rectangle. It's close, but it curves upwards because it the region that I got was taken by extending by dx right here. And so the extra area that I had is actually the extra area along the curve right there. And so what I've got is a curvy top. And so I have a thing that's not exactly a rectangle, but we agree it's pretty darn close. So I need to fix that fact by doing a more exact limit argument. And so I'm going to do that by going all the way back to my limit definition. So here is the proof of the fundamental theorem. And the proof is going to imitate the plausibility argument that I just made. If I let a of x be an area function, like so, then by definition, a prime will be the limit as h goes to 0 of a of x plus h minus a of x all over h. That's simply what it means to be a derivative. Okay. Well, what does this look like? Picture. Here comes f. Here is a. Here is x. And here is going to be x plus h. So that a of x is all of this area right here, but a of x plus h is all of this area right here. So a of x represents the area in red, and a of x plus h represents the area in green. Are you with me so far? Now what do I get when I subtract these two? When I subtract these two, all the stuff in red clobbers all the stuff in green, and all that I'm left with is this little piece right here. That's that thing that I estimated as a rectangle earlier. Okay? And I can represent that as the limit as h goes to 0 of, first of all, let me do the formal writing. Here's a of x plus h. Here's a of x. And using the additive interval property, I can split a of x plus h into two parts. The first part is the part that is a of x, and the second part is this part right here. And when I subtract, the stuff in red gets clobbered, so that what I'm left with is the limit as h goes to 0 of the integral from x to x plus h of f of t dt. Christine is concerned. Yes, sir.
So the a's just cancel.
It's not that the a's cancel, it's that the areas cancel. I want you to see the picture geometrically. The integral from a to x plus h is this whole area in green. The integral from a to x is the area just in red. Take this away, what are you left with? The area from x to x plus h. That's what's going on. So all of this is exactly like the plausibility argument that I made earlier, but in the plausibility argument I said, let's pretend this is a rectangle. Instead of pretending that it is a rectangle, what I'm now going to do is to appeal to my average value theorem. Because, and this reveals a condition that I didn't share with you, if f is continuous, on the interval x to x plus h, then there is a c in x to x plus h such that the average value of f is equal to f of c. That was my average value theorem. But what is the average value on this interval? The average value on this interval is 1 over x plus h minus x times the integral from x to x plus h of f of t dt.
Oh, snap.
You see it?
I see it.
He sees it. This average value that I've computed is exactly the thing that I've got right here. Zero. I'm taking the limit as h goes to 0 of the average value, and as h goes to 0, the average value on that interval is just f of x. Is just the value at x. That's it. What's the
So
that's
basically,
the
we just replaced the A and B with x plus h and x.
Yeah, that's right.
Okay.
I'm taking the average value over the interval x to x plus h,
Okay.
and so I did 1 over b minus a, interval from a to b, blah, blah, blah. But when I did, mathematically, it happened to be exactly the quantity that I was taking the limit of. See?
So the limit of h goes to 0. That's just another way to write the one at top.
Yes, that's right. So this is the limit as h goes to 0 of the average value of f. And if I am taking a rectangle, an interval of width 0, and I'm shrinking that interval down to a width of 0, excuse me, then the average value of that interval has only one choice. It's got to be f of x.
Hey, you see that?
Now, all of this was a fancy way to bring some mathematical rigor to the argument that I made here. The argument that I made here fully captures the spirit of it, which is that if I take a little piece of area and I divide it by the width, what I get is height. Remember, that was the same slogan, or the same concept that we used in talking about average height, or average height. Yes.
Well, first of all, what does even literal area mean?
It means how quickly am I accumulating area as x increases. I wish I could animate this, but picture that you're like walking along the x-axis, starting way back here, okay? And you walk in this direction, and as you walk in this direction, you pick up extra area. Okay? Yeah. So you're walking along here, and the question is, what is the rate at which you are adding on that extra area? And the answer is, I'm adding on extra area at the rate of the height of the curve. So if my curve is really tall, I'll be adding on a lot of extra area. If my curve is short, very little. If my curve hits the axis at 0, I add 0 area. And if my curve is below the axis, I'll actually be taking away area.
So does that mean if I have extra area, I'll go slower?
Ask that again?
Okay, I don't know what I'm gonna say either. No. There's extra area. So it's gonna take longer to go towards the end.
No. It's going to take, if my curve is really close to the axis, so that I have small f values, I'm going to have to go a far distance to get a lot of area. But if my curve is really tall, I can go a short distance to get a lot of area. So it's the rate of change of the area with respect to the distance along the x-axis that I travel. So there's no time involved here. It's looking at how the area changes with respect to how x changes. Or another way of putting it is that the extra area that you add will be proportional to the distance that you travel, and the proportionality will be the height of the curve. So if my curve is 3, then I will add area at the rate of 3 times whatever width I travel. And if the height of my curve is 6, I will add extra area at the rate of 6 times whatever distance I travel. Does that make more sense?
That's good. That's my
Okay. Good. Yes.
Can you go to the other slide?
Sure.
Scroll down.
Yep.
Oh, only your chance.
There we go. Yep.
Oh, I see that you just, okay, so the limit of h goes to 0. From the top one right
Yeah.
there. It's just basically taking the division of the h out and putting
Yes.
it on the side.
Yeah,
Okay.
that's exactly it. Yep. Okay. So how does this relate like to the number 2 that we had? How does this relate to something like this? Okay. I want you to observe that what we have here is like an area function, but it is not in standard form. So I can handle this in 2 different ways. First of all, I can handle it visually. And second of all, I can handle it with the properties of definite intervals that we have. If I handle it with the properties of definite intervals, then I can take my non-standard form and I can use, for example, the reversal property to put it into standard form. And now a little bit of constant multiple rule. Allows me to pull that to the outside, and now I use my slogan, the rate of change of an area function is the height of the curve. There it is.
Oh, where did t go?
Okay, so this is the second thing that students get confused about. The area function is not a function of t. That's the variable of integration. It's the dummy variable.
Oh,
The area
oh.
function is a function of x.
Okay.
And very importantly, the height of the curve that we're talking about is right at point x.
What is point X?
Who cares?
So how'd you get the E?
Because the height of the curve at x is e to the negative x. The height of the curve at x is e to the
oh, so you're
negative
doing
x.
Check the derivative.
No. What's our fundamental pair? The derivative. The derivative.
Oh.
Of the
Oh.
f
So you didn't do anything to it. You just took-
is the height of the curve.
Look what he did, guys.
And you can do
I knew
that.
that. I knew that.
That works. You don't have.
Look at that equals sign.
So why
And that equals
are we
8 prime X.
We've been doing this.
But we've been like taking derivatives and stuff. Just,
Sure. Like in
You
number
still-
2. In number 2, what did we do? No, still no.
We didn't have a formula.
That's right.
yeah.
In number 2, we didn't have a formula,
Okay.
but what did we do? We said that g prime of x was 1 minus.
Yeah.
No, we would never get that.
It's the same thing.
That's tough.
So the moral of the story is the fundamental theorem is nothing different from what we've been doing for the last couple of days. The only thing is we didn't realize its power.
It's just clean.
You guys are just impressed with the power.
It's like you just put like a fresh suit on it for a job interview.
Yeah, that's right. That's right. So let's make sure we get the power here.
Before it was walking around like, I mean. Did you just sound X?
It's just science.
Let's get it!
Yeah.
The power. I'm harnessing the power.
Because
Harness it.
here's the slogan: the rate of change of an area function is
The height of the curve. I'm harnessing the
That's
power.
it.
Well, do it. Do it again.
that's it. The rate of change of the area is the height of the curve.
I'm harnessing its power.
Excellent. Okay. Now I want to come back to the previous one. I think I moved a little too fast, but Here, we did it formally. We used the reversal property to put it in standard form, and we used the fundamental theorem like to do it. I want to also do it visually, so you can see what's happening. This function that I have right here is taking the curve e to the negative t, looks like this, and it is fixing a point 2, and it is letting our variable x change so that I'm integrating from x to 2. Okay? So that visually, if I increase an x by a little bit, what happens to the area? It decreases. By how much? By the height of the curve. So the rate of change of this function right here is the opposite of the height of the curve because I'm starting at the left end and pushing in.
That's why.
You see it? Yeah.
So negative e to the negative x is g prime, right?
Is the rate of change of the area function.
Okay.
Yeah.
Yeah, okay.
Yeah.
Ooh.
But that's really difficult.
Oh.
You know, I
Yeah.
want to smack that
Well,
guy.
mine's always-
Okay.
Now, that's just really-
Let's look at one more that's a little strange.
What if we take it tomorrow?
That's definitely- Oh, that- you gotta just let it. You gotta just let it in there like going hurt. But we all heard it. It's crazy not to. Oh my God.
That's true.
Yo, I wasn't. If you look at my stomach.
Okay. So, these kinds of things show up sometimes, and they are legitimate in various applications. Ooh, so, let's keep in mind what's happening here. What I have here is a function of what variable?
X.
It is a function of x. So I can say that if I want to write it formally, that a of x is equal to.
Hold up.
Yeah.
What is the purpose of the dummy variable? Is that just to mess with us?
No, of course not. The purpose of the dummy variable is that I've got some curve right here,
Yeah.
and I need to represent the relationship between the horizontal points along the curve and the vertical points along the curve.
Yeah.
Okay.
But when I have this variable x, that variable x is telling me, well in this case it's starting at 2 and going out to x, it's telling me how far out I'm integrating to.
Yeah.
And how far I'm integrating out to is not the same as that variable right there.
Okay.
Okay, so I've got this area function, but this area function is a function ultimately of x squared, right?
Yeah.
How am I going to deal with that? I'm going to deal with that by doing chain rule. Let me show you in slow motion, and I'll come back and do it quickly. If I want to think about it in terms of chain rule, I can pull off a substitution. I can say that a of w is the integral from 2 to w. There's my standard form, and w is x squared. Just pulling off that substitution right there. So that a prime of x should be equal to dA dw times dw dx, using my chain rule. In other words, derivative of the outside times the derivative of the inside. And because this is in standard form right here, this is automatically the height of the curve. And because w is x squared, its derivative is 2x.
Yo, I got it. Let's get it. Let's get it.
Yeah. So that what I get is the height of the curve times the derivative of the inside. Now here I did this with a formal substitution, but actually we don't need to work nearly that hard. We recognize that the derivative of an area function is the height of the curve, and the height of the curve at our particular point is like so, times the derivative of the inside function.
Ooh.
Yo, where's my favorite?
Outside,
Yo,
inside.
his paper says that.
Cool.
Good for you.
Good job, Dave.
I'm trying to.
No one way. Oh, so you're just using substitution?
Yeah, I'm just using substitution to make it a little bit more clear why this should work out as outside, inside.
Okay.
So really, we can just think of the fundamental theorem as one more derivative rule. Area functions are a family of functions, and their derivative is the height of the curve. Yeah.
So, that, what you just did, the chain rule only applies when it's like an exponent,
No, it would apply to any function whatsoever, right here.
So if it was his x, it would still apply to him,
Sure, yeah, because the derivative of just x is 1, and therefore invisible. All right, check and see if you got it. This is about as abstract as I can think of. What is it? Take a minute. Take a minute, write it down. And then you can compare yourself. Okay. Outside
I got it.
times. And it's all on tape.
Yeah.
That's awesome. Did you guys all get it?
Yeah.
Good. Good. Very good.
Whoa.
No.
Let's do it.
Flip. Question.
Oh no.
You're good. Okay.
That's
That's it. Hey, I'm really excited. You guys are doing well.
Why isn't it the derivative of the outside?
Here. We're here. First, back or second? First one? The first one. Because the derivative of an area function is the height of the curve.
Oh my goodness.
Yep.
Oh, dirty. So just instead of x being on top, then just u.
Yeah. And it's evaluated at that point.
G of x is the height.
Actually, f of x is the height.
Oh. Nah, I was trying to relate it. Because at the height of the curve.
Yeah. Got a lot of curves going on there.
Yeah.
I'll see you guys tomorrow.
Is that going on the